We've talked before about flat spacetime here, but before we can graduate to the curved version and general relativity, we need a stronger foundation in spacetime geometry. So today, on Spacetime, it's spacetime. To begin, here's a heads up. Today's episode will reference information from 3 of our earlier episodes. To avoid getting lost, you should pause me and watch them now if you have not already done so. All right? Here we go. In the episode on curvature, we saw that tiny patches on the surface of a sphere look like the Euclidean plane. Since we know how to draw straight line segments in a plane, then we know how to do that in tiny patches on the sphere. So, draw tiny straight segments over a series of tiny patches, join them, and voila, you have a geodesic on the sphere. Eventually, we want to do the same thing in curved spacetime. However, tiny patches of curved spacetime don't look Euclidean. They look like flat spacetime, which, although not curved, still has a geometry that doesn't always agree with our visual intuitions. So we won't know what to do in each tiny patch unless we first understand what straight line, tangent vector, and parallel mean in flat spacetime. Clarifying that is the goal of today's episode. Now, we're not going to do a complete treatment of special relativity or all aspects of flat spacetime geometry. We're not even going to get close. That's fascinating stuff that you can learn about from other links in the description, but I only have a few minutes and I need to stay on task. You guys ready? Awesome. Let's get started. Our principal tool for exploring flat spacetime geometry will be something called a spacetime diagram for representing physical events. Here's how it works. Pretend the world has no gravity, Newtonian or otherwise. I'm not glued to Earth's surface, the moon doesn't orbit Earth, in fact there is no Earth since Earth is held together by gravity. This gravity-free world is what flat spacetime describes. To record when and where events in this world happen, I've got a clock to tell time. Nice. And I've got an infinitely long stick with tick marks on it attached to me at the x=0 mark, my own personal x-axis. My clock and my axis together make a frame of reference, which should also have y and z axes, but I want to keep things visually simple. To represent this setup in a diagram, let's copy my x-axis onto a blackboard and add a vertical axis to show the time on my clock. Actually, that vertical axis is showing the distance ct that light travels per tick of my clock, which is interchangeable with clock ticks since I know the speed of light. I know that seems like an awkward way to record time, but you'll see in a minute why it's convenient. Now recall from our earlier flat spacetime episode that points on this blackboard are not locations in a two-dimensional physical space. Rather, they are events, each of which occurs somewhere along my axis in a one-dimensional physical space and at some moment according to my clock. Is my frame of reference inertial? Well, let's see. I release a ball, and it just hangs there. So yes, inertial frame. All right, now some weirdo in a red shirt carrying his own clock and x-axis approaches me from the left at constant speed. He passes me just as my clock reads 0, and at that same moment, I shoot a photon from a laser pointer to the right. And oh yeah, this guy's towing a monkey. Anyway, say I plot the values of CT on my clock as the photon passed different marks on the x-axis. I get a nice 45-degree line, thanks to the funky vertical axis units I was using. If I do the same for the guy in red, I also get a line, but that one is more vertical, since he moves slower than the photon. In the same amount of time on my clock, he passes fewer marks on my x-axis. Those lines that we just drew link all the events at which the photon and the red guy, respectively, are present. They're called world lines, and they represent the entire histories of things. Things like that monkey. He's perched at a fixed spot on the red guy's x-axis, and so he moves with the same constant speed that the red guy does. So the monkey's world line is also a line parallel to the red guy's world line. What about me? I am at x=0 for every event at which I am present, so my world line is vertical. It coincides with my time axis. But it's only vertical from my frame of reference. Red guy also has a frame of reference, and from his perspective, the diagram looks like this. See, according to him, the photon also moves rightward at speed c. We agree about the speed of light, so its world line looks the same as in my diagram. But red guy says that I'm moving, not stationary. I'm moving to the left. So my world line isn't vertical, it points slightly backward. Instead, red guy's world line and the monkey's world line are vertical in his diagram, since they're both stationary from this perspective. Now, on either diagram, I could also have drawn lines that are more horizontal than 45 degrees, but they wouldn't be world lines. Because to be present at two events represented by points on such a line, an observer or a photon would have to be moving faster than light, which normal objects and photons cannot do. Now, spacetime diagrams are great for visualizing cool phenomena like time dilation or length contraction or disagreements between observers about event sequence. And that's fun, but it would take us off course. Instead, I just want to use these diagrams to establish how parallel transport works in flat spacetime. Because here's the thing, the answer is not clear a priori since you can't trust your eyes in space-time diagrams. Watch this. These highlighted points in my diagram and in the red guy's diagram correspond to the same events. So those are the same points, and thus these are the same line segments in spacetime. Yet between diagrams, their visual length and the angle between them have changed. If you throw in the perspective of a pony flying to the left super fast, looking at the same events, different again. So what's going on? Well, spacetime diagrams preserve the spacetime interval between points with its weird minus sign, not the Pythagorean Euclidean notion of distance that seems to be hardwired into our eyes and brain. So while these diagrams help quasi-visualize things, spacetime doesn't really look like this. Now that's not surprising, but it is disorienting since we rely so much on our eyes. But notice that visually parallel lines do remain visually parallel in all three diagrams. The visual separation between lines may change, as does their tilt, but they're always parallel. So the visual criterion for parallelism works, since it's either met or not met in every frame of reference. It also happens to work for vectors. So now we're finally in a position to state some things that may have seemed visually obvious, but that I don't think really were. For starters, this spacetime really is flat. Parallel lines stay parallel. Second, the world lines of the red guy, the monkey, the photon, and me are all straight. All of their tangent vectors remain tangent when parallel transported, so all of them are geodesics. However, not all world lines are geodesics. Suppose I see a car approaching me, slowing down, turning around, and speeding away. A tangent vector to its world line doesn't stay tangent under parallel transport, so it's not a geodesic. And this is interesting. In Newtonian mechanics, we distinguish inertial and non-inertial observers dynamically by using the floating ball test. But in spacetime, we can also distinguish those classes of observers geometrically. Inertial observers have geodesic world lines, and non-inertial ones don't. And that's kind of the whole point of talking about spacetime in the first place. By representing dynamical phenomena from the physical world as geometric objects and relations in a tenseless mathematical space, we can discover facts about physics just by exploring geometry in that space. It's kind of cool. I want to wrap up by going back to tangent vectors for a second, because I haven't told you yet what they represent physically. In a more standard drawing of motion over time, like what you might see in a Physics 101 class, tangent vectors to trajectories represent velocities, how fast you're going and in what direction. But that interpretation doesn't work on a space-time diagram. Think about it. Motion is relative. In my frame, my own velocity is 0, but in the red guy's frame, it isn't. So ordinary velocity would not be a frame-invariant geometric vector in spacetime. Also, things don't move through space-time. It's not this kind of space. Instead, we want to represent some aspect of dynamical motion over time through space as a static geometric object. The question is, how do we do that? Well, without justification, which would take us too far off topic, here's what turns out to work. Instead of tracking changes in the monkey's position on my axis with respect to ticks of my clock, that's ordinary velocity, I'm going to track two hybrid quantities instead. The monkey's position on my axis relative to the monkey's clock, and the time on my clock relative to the monkey's clock. That, it turns out, if I stack it, is the tangent vector to the monkey's world line. It's called the monkey's forevelocity, even though that's a bit of a misnomer since there's no motion through spacetime, just a term. And more interestingly, the length of that vector, at least in the sense of spacetime interval length, is minus the speed of light squared. In fact, every observer's forevelocity always has a length of minus the speed of light squared, even the accelerating car's forevelocity. So if we call the spacetime length of a forevelocity vector a spacetime speed, then the world line of every inertial observer is a constant speed straight line. That's what I've been meaning all along. And accelerated observers' world lines are constant speed non-straight lines. Chew on all that, because it's our departure point for talking about curved spacetime in the next episode. And none of this is obvious, so I hope you see now why I took this detour. I know it's a lot to take in, but you've got a week to mull it over before we plunge head first into curved spacetime.